And welcome to Computer Science E1, Understanding Computers and the Internet. My name is David Malan, and I will be your instructor this semester. So each of you have in your hands, hopefully, one of these floppy disks. And as much thought as some of you gave to choosing your color, I'm afraid we're about to destroy precisely the disk that you took some pride in accepting. So with that said, what I'd like you to do is go ahead and take your favorite color disk, and go ahead and take your thumb and index finger and pop off the black cover that is on the bottom of the disk. And watch your eyes, since there's a bit of a spring that can sometimes pop out. So we are about to see how a floppy disk works. This is not how you should normally use these things, needless to say. The funny thing is, we went with the fancy disks this year, and as such, I think have sort of spoiled the surprise that you can actually see inside of the disks without doing what we're doing. But you notice probably a little circular something or other in there. Well, what you're seeing is some white pads of sorts, but what the juicy stuff is now this black piece that if you push your index finger down on, how would you describe the feel?
Very soft.
Very soft, or one might say plastic or floppy. So these are floppy disks after all. They've always felt pretty hard, but go ahead and just insert two of your thumbs or other fingers and pop open the whole case itself. And what you now hold in your hand is literally a floppy disk. All the plastic cover is protection of sorts, and all that little felt pad is further protection against dust and so forth. But for the most part, these are a fairly cheap medium, and they're a small medium. They don't hold all that much information. For those of you who are just joining us, if you'd like to catch the eye of one of our teaching fellows here, we have a little parting gift for you. These are particularly small in the amount of data they can store. Does anyone know just how much information you can store on this so-called floppy disk? 1.44 megabytes. So 1.44 megabytes. Let's see, without even teaching this stuff yet, if we can take this a bit further. What does 1.44 someone else megabytes mean? Good, we already have the looks of fear. That means you're in the right class. A million bits. Okay, so roughly 1,440,000 bits. So for now, let's just tease apart one of the pieces of this term, megabytes. So mega, henceforth, just denotes million. So whenever you say mega something in this context, you mean millions of something. Well, what do we mean when we say megabyte? Well, we mean millions of bytes. Now, we'll get to what a byte is in just a moment, but roughly these disks store over a million, roughly 1.5 million byte, or 1.5 million bytes. All right, so now, what's a byte? Okay, so a 0 or 1, not quite. You're on the right track, but you went smaller, to a smaller denomination.
Well, it says 8 bits, and I said
Well, of course, all of the answers tonight are on this yellow handout. Yes, it does say that there are 8 bits in a byte. So what is a byte? Well, apparently it's 8 bits. Well, what do we mean by a bit? Well, I'll answer it myself. As this gentleman said, a bit is just a 0 or a 1. Now, even if that's sort of an abstract concept, you've probably at least heard. Even if the computer on your desk scares the heck out of you sometimes, especially when things go wrong, you probably know at least that computers only understand what two numbers in the world? Zeros and ones, right? So they only speak zeros and ones. They only speak so-called binary. Bi meaning two, so binary just means they can only understand zeros or ones. Humans, by contrast, when it comes to numbers, we can understand 0 through 9. So we understand decimal, dec, implying 10. So we understand 10 digits. Computers only understand 2. So what is the relevance then of bits to this actual floppy disk? Well, data, whether it's your resume, whether it's some file you've downloaded, whether it's some photograph in digital form, ultimately boils down to a whole bunch of bits. In other words, if you're looking at a web page, that web page is comprised of a whole bunch of bits. Some of those bits represent text. Some of those bits represent images. Some of those bits might represent sound. But at the end of the day, anything you see on a computer or do with the computer boils down to zeros and ones. So if you drag to your A drive, to your floppy disk drive, your resume, resume.doc, a Microsoft Word document, effectively all that file is a bunch of zeros and ones. And they're laid out in a pattern that Microsoft has decreed represents a word processing document. How they're laid out isn't that interesting, and we won't even dwell on how zeros and ones are laid out, but just suffice it to say that a resume boils down to patterns of zeros and ones, and clearly, somehow, those zeros and ones represent letters, for instance, of the alphabet. They represent bold-facing somehow. They represent italics somehow. All the stuff that you're familiar with, but for now, just take it for granted that all of that stuff is ultimately represented as zeros and ones. So if you drag that resume.doc to this floppy disk, you are dragging the bits that comprise that file to this floppy disk. And you're using up some of those 1.44 million bytes, or rather roughly 9 million bits, if you multiply 1.44 times 8, since there's 8 bits in a byte, but we'll come back to that, don't worry. You're putting those bits on this disk. You're putting those zeros and ones on this disk. But where are they? Right, this is all there is to a floppy disk. Where are these zeros and ones?
Encoded on there with light.
Okay, encoded on there with light. Not a bad guess, not quite right, but they are encoded on here somehow. Yeah? Yeah, so they're encoded magnetically, and that might all of a sudden dawn on you if you've thought or ever been told, don't leave floppy disks, at least years ago. Don't leave them too close to a big magnet. Don't put them near a refrigerator. Now, people have long worried that if they run their floppy disks or their laptops through airport security in an X-ray machine, that's okay, right? So long as the machine's designed correctly. X-rays are not necessarily magnetism, so it doesn't necessarily distort your data, or at least it shouldn't, but it all boils down to something magnetic. And if I do this with my 2 fingers, I have literally, in a sense, wiped off some of the bits from this disk, because though we as humans can't really see them, there are some 1.44 million, or rather almost 10 million bits. There are almost 10 million magnetic particles on this disk. They're pretty darn small. You can't see them, but they're laid out in a way that represented, up till 5 minutes ago, my resume.doc, for instance. Well, what do we mean by magnetic particles? Well, this is already getting a bit technical, so let's try to make it a little more real. You might remember this guy, Wooly Willy. So Wooly Willy, if you've never used him before, has a whole bunch of magnetic particles down here. And what you can essentially do with this red stick, which is just a magnet, is drag those magnetic particles and give him eyebrows, or give him a beard or a mustache or so forth. Well, in effect, these are pretty small magnetic particles. Well, similarly on that floppy disk are there magnetic particles, and they're even smaller. There are not even 1.44 million or so magnetic particles in this little toy, but there were, up until a few minutes ago, on that floppy disk. And so when you put a floppy disk into your computer, and again, drag that resume onto the disk and let it copy, what you're essentially telling the computer, what you're telling the computer's floppy drive to do, is just lay out these magnetic particles in such a way that some particles represent a 0 and other particles represent a 1. In the simplest scenario, think of it this way. You probably know, or at least vaguely back from high school or so forth, that you can have, when you have something that's magnetically charged, there's a positive end and a negative end. Maybe that much perhaps comes back from physics. Well, just think of it this way. What's an easy way of representing zeros and ones then with magnetic particles? Well, if it's this way, maybe positive end up, negative end down, let's say it represents a 1. If you flip the thing around, let's say arbitrarily it represents a 0. And so using just simple magnetic particles, can you effectively represent zeros and ones on a disk? Yeah?
Would it be laid out like a record?
Good question. Would it be laid out in a record? The short answer is that it depends on the particular technology, but yeah, for the most part, floppy disks are laid out in concentric circles so that when they're spun in a drive, you can read them as efficiently or as linearly as an old phonograph would of a record. Questions in addition to that one? Okay, that was meant to take some of the fear factor out of how computers work, boiling it down to, of course, Wooly Willy. And perhaps would it help further if I pass this around and we use this as our first demonstration? You got 2 hours to play with Wooly Willy, so if it makes its way up to the top, that's fantastic. We got a whole bunch of other stuff that we'll pass around shortly. For now, let's keep things a little serious for a moment and consider some of the other basic building principles here. And just to give you a teaser here, what we'll do tonight is, one, we're going to get some of the cool stuff out of the way, cool from a computer science perspective, in that within just a few minutes' time, not only will you understand, hopefully, if we did that well, how data is essentially stored on a floppy disk, in just a few minutes' time, you will also know how to count like a computer. You, in a few minutes, will be able to speak binary. That is, in terms only of zeros and ones. But before we get there, let's start with a simple question. Just how do computers go about counting? In other words, I said on that floppy disk, data ultimately boils down to zeros and ones. Even if it's your resume, even if it's letters of the alphabet, computers only understand zeros and ones. Therefore, it stands to reason that a computer has to be able to somehow use zeros and ones to represent letters of the alphabet and so forth. So how might that happen? Well, if you have just one magnetic particle, one bit, if you will, how many different values, how many different numbers can you represent using one magnetic particle? Two, right? We've sort of addressed those already. What are the two values that you would usually represent with just one magnetic particle? 0 and 1, right? It's either this way or it's that way, and after that, you're sort of out of options. Well, how can we go about representing larger numbers and clearly doing things more interesting than only understanding zeros and ones? Well, we can liken this to an example of an abacus. We're not going to teach you how an abacus works, but you probably at least know that an abacus works to allow one to perform various types of mathematics by sliding these beads up and down. Agreed? So let's take a computer version of an abacus for just a moment. So we're taking the abacus. Doesn't matter how the abacus works. What matters is how this thing works. This is similar in spirit to an abacus, is in that think of it as a wooden device, and it's got some beads that can go up and down on little poles. And we're going to use this analogy to an abacus to propose how you can count higher than the number 1 while still using only zeros and ones to represent information, to represent those values. So take a look at the following. On the far right, there is a bead that's currently in the down position. Henceforth, if we ever see a bead that is in the down position, it will be said to represent a 0. So the magnetic particle, in effect, is down. By contrast, if you look at the second bead all from the right, that is up, that will henceforth be said to represent a 1. It's as though a magnetic particle, in the world of floppy disks, is instead up, and so forth. Hold that thought for a moment and think about now, forget high school physics because I saw even some blank stares there. How about we'll go back to grade school arithmetic. And when you wanted to represent the number 123, and you maybe wanted to perform some addition with it, well, what does it mean to write down the number 123? Well, you probably recall that each of these numbers, and just the number 123, sort of represents something. This we used to say was the ones column. So this we used to say was the tens column. This was the hundreds column, and so forth. So why do the digits 1, 2, 3 in our world of decimal, that is in everyday real life, represent the value 123? Well, we've got 1 100. We've got 2 tens, so that's 20. So 100 plus 20 plus how many ones? Well, we have 3 ones, so 123. Right, it should be that simple. If you're wondering where the magic is, there really is none, because this is how we all probably grew up. But now liken it to the world of computers. Computers only understand 2 values, zeros and ones. We understand 10 values, 0 through 9. But how can we borrow the same logic and represent numbers like 123, but using only the digits zeros and ones? Well, what we'll do instead in the world of binary is say that the rightmost column is the ones column. Let me go over here since we're getting cut off here. We'll say that the right column is the ones column, but we're going to say that the next column is the twos column, and the next column is the fours column, the next column is the eights column, 16s column, and so forth. You can probably see the pattern. Over here in reality, you usually multiply by 10. Computers, to represent numbers, are instead multiplying by 2. We're just multiplying by 2 every time. So this abacus up there is effectively representing a number just like we were representing 123. In other words, this number up there has what? Well, 0 4096s, 0 2048s, but how many 1024s? 1, right? Because there's a 1. The beat is up, which represents a 1, so that gives us 1024. How many 512s do we have? Okay, so we have 1 512. How many 256s do we have? 256. How many 128s do we have? All right, 128. How many 64s? Okay, 64s. How many 32s? Okay, how many 16s? 16s. 8s? I heard discrepancies. How many? One. All right. 8s. How many 4s? Okay. How many 2s? Okay. How many 1s? Okay. 0. All right. It's really hard counting backwards and divisors of 2. So, what number is being represented by that sort of faux abacus? 1998, which is the year in which I invented this demonstration. So, 1998. The fact that it's 1998 is not what's interesting. But is it clear why those beads in that arrangement can be said to represent the value 1998? And just to reinforce it, if it's not, just think back to this example. Why does this represent the number 123? Because it's 1 100s, 2 10s, and 3 1s. The logic is exactly the same, but we can only count as high as 0s and 1s. Well, what is the relevance now to the world of computing? Well, we talked about bits being stored on a disk in terms of magnetic particles, 0s and 1s. We're going to move away from the wooden beads on poles now, example. We're going to move back into the world of computers. Computers store information similar in spirit to that simplified abacus. They store numbers, big numbers, like 1998, just by storing sequences of 0s and 1s. And if you look at that sequence of 0s and 1s together, maybe 8 bits, 8 zeros or 1s at a time, together those represent another, just like that abacus on the whole represented one big number. And computers do this by way of effectively little light bulbs. So again, a simplification for a moment, but computers, as you may have heard, have lots of transistors. Right? If you read about CPUs, that is the brains of computers, you often hear these crazy statistics like Intel now has millions more transistors crammed into their Pentium 4 processor. Well, a transistor is a piece of hardware whose inner workings we won't explore in this course, but in effect, it's a switch. It's either on or it's off. It's like the lights are either on or they're off. In other words, it's like a light bulb. It's either on or it's off. That's all a transistor is. So using these tiny little devices called transistors, computers can effectively, in a non-magnetic way, represent the same idea. 0s and 1s. If a computer turns on its transistor, that is, turns on the light bulb, that computer is now storing the number 1. If it shuts off that transistor, that is, turns off the light bulb, it is now representing the number 0. So think of it now this way. If a computer wants to represent a number more interesting than just 0 or 1 itself, but bigger numbers, like 1998, all you need is a bunch of light bulbs. And you need to think of those light bulbs perhaps being in a straight line, where each light bulb represents a different column. Just like on our board example, the digits were in different columns. So with that said, if each of these light bulbs right now represents 1 bit, each of these light bulbs is off. So a white bulb in our overhead example just represents the value 0. If it's instead yellow, that means the light is on. So we have how many of these light bulbs up on the screen? Okay, we do have 8. And in small print, you can see it perhaps on your handout, I did give you the column headings for each of those light bulbs, from 1's column to 2's all the way to the 128's column. If all of these light bulbs are off, and there's 8 of them, and they're arranged in those columns, what number is being represented by these 8 light bulbs? Right? That's an easy one, right? They're all off. It clearly represents 0. We can be really anal about it and say, well, we have 0 128s, 0 64s. The story is the same, but the answer remains 0. What if instead we lay them out like this? What number does this represent? Okay, 1. Why does this represent 1? Well, how many bulbs are on in the 1's column? 1. And how many in all the other columns? 0. So if you do out the math like this, you end up getting 1. What if we turn on this light bulb? What number does that represent?
0.
So I heard 0 and 2. Do I hear another 0? Then we'll be evenly matched. So this is in fact 2. Well, why is that? Well, let's start from the left and belabor the point. Well, on the left we have 0 128s, 0 64s. Fast forward now to the second to last bulb. How many bulbs are on in the 2's column? 1. So we have 1, 2. How many bulbs are on in the 1's column? 0. 0. So if we only have 1 light bulb on, and that light bulb is in the 2's column, it just represents the number 2. So quick review. Where are we at right now? What did the first column represent? 0. 1, 2. Okay, pattern. What about this one? 3. What about this one? 4. So in effect, you have just learned how to count in binary. Now granted, we're talking about light bulbs for a moment, and not zeros and ones, but mentally, go ahead and replace these light bulbs with, let's save that example for a moment, replace these light bulbs with zeros if they're white, ones if they are yellow, and how then would you represent in binary, that is using the numbers zeros and ones, what we know as the number 4? And you can steal the answer off the slide. Good. 5, close. Good. 1, 2, 3, 4, 5, 1, 0, 0. So in other words, if you can start with tonight's lecture and see in that crazy pattern of zeros and ones what we as humans know as the number 4, you can now think, in effect, like a computer can. Underwhelming, isn't it? Well, let's put this into context. Why is this useful? How do computers actually make use of this representation of zeros and ones and do something with these kinds of values? Well, think about the simplest of computers, a calculator, like this one here. A calculator, at the end of the day, especially the ones that are made today, are pretty much like dumbed-down computers that only do a few things: addition, subtraction, multiplication, and so forth. Certainly ones that just have so many buttons, not terribly many. We're not talking scientific calculators or graphing calculators. So when you go ahead and perform some computation like 2 plus 2, well, what is probably happening inside this device? If I take this calculator and hit the number 2, what in real-world layman's terms happens when I hit the number 2 on a typical calculator? Literally, treat me like an idiot. What happens? I hit the number 2, just this once though. Okay, 2 appears on the screen. Right? It's that simple. But 2 stays on the screen. Right? At least if the calculator stays on, 2 stays on the screen. What that implies then, perhaps, is that the calculator is somehow remembering what I typed in. And it's displaying it to me constantly. Well, how does a calculator remember what I have typed in? Well, inside of a calculator are tiny chunks of memory called registers. Or we can think of them as what are called registers. And we're going to build up from this in a bit to what you know as RAM and memory on a higher level. But for now, for simple devices, calculators have registers, which is to say a calculator might have maybe 5 registers, chunks of memory, each of which has, let's say, 8 transistors inside of it. So for the sake of discussion, a register for tonight's purposes will be said to be just a cluster of 8 transistors. Well, transistors were just these switches, that is, light bulbs effectively. So if you have 8 transistors at your disposal within each of these registers, just by turning certain transistors on and turning certain other transistors off, you can effectively represent numbers, like we did with 0 and 1 and 2 and 3 and 4. So if I punch in the number 2, well, what's inside this transistor? If we blow it up, what's inside this register? If we blow it up, we essentially have 8 light bulbs. And if I hit the number 2, which of these light bulbs is going to turn on in order to remember the fact that I hit the number 2? Perfect. The second to the last one gets turned on, and everything else stays off. That is, no electricity is used, or no electricity passes through the other transistors. We just throw that light bulb on. So if you're having trouble thinking in zeros and ones, keep thinking about light bulbs for now. We throw on one light bulb. If I then hit the plus key, well, the calculator similarly remembers that I hit the plus key because eventually it's got to do some math when I hit the equal key on the keyboard. So I hit the plus key, and somehow or other the calculator is going to remember that I hit plus. How it does that, we'll ignore for now. Let's focus on numbers. Now I go ahead and type in, let's say, the number 7. Well, that 7 is going to get stored in this third register. All right, let's blow that up for just the sake of discussion. So I now have 1, 2, 3, 4, 5, 6, 7, 8 light bulbs at my disposal. I have typed in 7, so what is this calculator going to do to remember the fact and display on the screen the fact that I typed in 7? Excellent. The last 3 go on. Good. So we only taught you how to count up to 4, but some of you are already bootstrapping up to 7. Why does this represent 7? Well, 1, 1, 1, 2, 1, 4, 4 plus 2 is 6. 6 plus 1 is 7. Ergo, this represents the number 7. That's all. No magic. All the calculator has done is thrown the equivalent of tiny little switches or light bulbs inside of its so-called registers to remember the fact that I hit 2 first, and then I hit 7. Well, as soon as you now hit the equal sign, the number 9 is going to end up being displayed on the screen. And so finally, in our climax here, what is going to be stored in terms of light bulbs in this sequence of 8 bits in the fifth and final register? Okay, the 8 and the 1, that's easy, but what does that mean? Which one? Good. So the fourth one over. These stay as zeros. These, of course, stay as zeros. Why is this representing 9? This is the 1's column, 2's, 4's, 8's column. 1 8 plus 1 1 is 9. Right? By now it's probably getting boring. And that's kind of a neat thing. If 20 minutes ago you would have no clue, perhaps, what these numbers even represented. So take comfort in your boredom right now. With that said, let's task you with something that's a little sillier. What is this representing? Top row is representing 9.
0.
And I'm going to cheat. Give me just one moment to back up for something here. Little hint? Okay, it is 90210. Convince me that you don't just remember the song. Why is this representing 90210? Well, let's convert this thing to bits. So now the light bulbs just became 1s and the off light bulbs just became 0s. Well, the top row I already heard earlier is representing 9. That's nice because we already saw that one a second ago. 0 is the second row. 2 is the third row. 1 is the fourth row. And obviously the fifth row is 0. A little bit of temporary, if dated, pop culture with our little binary discussion here. Yeah, question?
Isn't there any permutation of these 1s and 0s that you can't get some number that you want?
An interesting question. Is there any permutation of 0s and 1s such that you can't get the value you want? Well, that is an interesting question. Let's think about this calculator, because right now it's a pretty cheap calculator insofar as each register only has 8 bits worth of storage. Which begs an interesting question. If you only have 8 bits, that is 8 light bulbs that you can turn on or off, what is the biggest number that this calculator is capable of understanding? 128, I heard. I heard 255.
128 plus 64 plus 32 plus 60 plus 8 plus 12 plus 1.
Okay, so what she said, right? 128 plus 64. Add all those up, and you do get what someone else did say, which is 255. In other words, if you have 8 bits at your disposal, well, we can look at this another way. If you're mathematically inclined, if you have 8 different placeholders, and each place can take on 2 values, well, you have 2 possible values here, times 2 possible values here, times 2, times 2, times 2, times 2, times 2, times 2. Well, that, and don't get scared by the math, we'll move quickly away from it, is 2 to the 8th. 2 to the 8th is 256. Wait a minute. And if you don't believe me, just take it on faith that 2 to the 8 is 256. But we just said that the biggest value we can store in this calculator is 255. How do we reconcile this? So what's the smallest number we can represent? So 0 is the smallest number we can represent, and we said that in our 90210 example here a moment ago. So if the smallest number you can represent is a 0, but you can represent 256 total values, look, obviously the biggest number you can represent is 255. We won't dive into this just now, but at the risk of throwing you for a loop, we're kind of forgetting one very important feature of even the cheapest of calculators. How many numbers it can display, which in effect is related to how many bits it can store per value. But what is this calculator, given our assumptions right now, incapable of understanding or computing with? Say it again? Negative numbers. Right? That's kind of a reasonable thing for a calculator to support, and I'll leave it as a brain teaser for now. We don't seem to have built in any support in our notion of binary right now for negative numbers, but it is in fact possible. But let's first just summarize here. Allow me to, I'll even put our little theme song on here, and go ahead, if you would, and jot down for me, just as for the sake of reinforcing this, the blank cells in the right column, all of them except the ones labeled ... What we want is, on your lecture notes is fine, the sequences of zeros and ones that in binary, which is also called base 2, represents the decimal numbers, that is base 10, on the left-hand side. So in other words, I'll give you the first one. How do you represent 0 in binary? 0. Okay, I'll give you a minute or two. Oh, it's okay. We'll take it from the video. Probably not. Okay, sure. Just remind me. And even as you finish up, go ahead. If first day of class can always be a bit awkward, especially if you haven't taken classes in a while, take this as an opportunity now to casually glance over your shoulder at the other person next to you, either to your left or right. This is rare that this is academically acceptable, but go ahead and introduce yourself, if you would, to the person on your left and or right, and just compare answers and see if either of you have goofed. No shame in doing so. All right. So now you get the benefit of both of you. How do you represent 0? Well, I did that one. How do you represent 1? 1. How do you represent 2? 3? 4? Okay, 5? 6? And 7? 1, 1, 1. ... 15? I heard a 0 in there somewhere. So 1, 1, 1, 1. Agreed. If you're not quite convinced, just again, do the math, right? 1's column, 2's column, 4's column, 8's column. Should give you 15. The next one was 255. 1, 2, 3, 4, 5, 6, 7, 8. And finally, in sort of a nice example when we can no longer use just a byte of bits, but rather we probably need 2 bytes, or at least 9 bits, how do we represent this? 256.
All 1s, 7 zeros, and a 1?
All 1s, 7 zeros, and a 1. Much simpler than that. Think about the pattern. If you have the 1's column, double it. 2's column, double it. 7 zeros and 1, and then 8 zeros, sure, or just simply keeping the same pattern here, we need 1 bit, 1 light bulb in the 256 column, which comes after the 128 column, right? Just continue the pattern of doubling, and then we need 1, 2, 3, 4, 5, 6, 7, 8. So what is the significance of computers using bytes as sort of the fundamental unit of storage? Well, for the most part, computers do store data in terms of bytes, which is to say, if we really wanted to be accurate with writing these numbers down, we would want to write out 8 digits for each of these values. It just so happens it's a little cleaner doing it this way, because if we did want to use an entire byte to represent the number 1, what would I have had to what should I have written down? 7 zeros and a 1, and that's fine. And in fact, a computer would in effect waste 7 light bulbs just to store the value 1, because the fundamental unit of storage in most computers is an entire byte. It doesn't use just individual bits or transistors. It uses an entire byte of information. Sometimes, if though you want to represent even larger values, you need to use multiple bytes, and that's fine. But similarly there, might you have some wastage? So if some waste, if you have the number 256, well, how many bytes do we need for that guy? 2. Just so happens that to be really particular, we need 7 zeros before this thing. The 8th bit in the first byte is a 1. Then we have another byte of all zeros. How many bytes do you need if you want to represent the number 4 billion? Oh, okay, this is E1. That is an acceptable answer. We'll come back to that in a moment. Let's answer it for ourselves. These are not the sorts of numbers that you will ever need memorized, but they should give you a sense of the magnitude of these common prefixes. So we have a little table here that just gives you a quick cheat sheet as to what some basic units of counting are in the world of computers. So we already talked about bits, and the definition of a bit is that it's a 0 or a 1. We talked about bytes. Its abbreviation, incidentally, is a capital B, whereas the bits abbreviation is a lowercase b. Sometimes even advertisements in like Best Buy's catalog will get these things wrong, but you'll learn over the course of the semester when you should assume they mean bytes instead of bits. And it's relevant, right? If you buy something that says capital B when really the box should have said little b, it means you got 1/8 as much as you paid for. So buyer beware. Well, what is the definition of a byte? Well, it's just 8 bits, or 8 little b. If we wanted to write it gently in abbreviated form. Well, what about the next one? What do we call a collection of 1,024 bytes? Kilobyte. Now, it's not quite 1,000, but 1,024 is almost 1,000. And what prefix do we usually use? Metric system, for instance, to denote 1,000? Kilo. So that is a kilobyte. What happens when we have roughly 1 million bytes, as in the 4th column, 4th row? Megabyte, M-E-G-A. What about in the 5th column when you have roughly a billion bytes? Yeah, a gigabyte. So you've heard all of these terms before, and all they are increasing orders of magnitude. So just to be clear, we have kilo, we have mega, we have giga. And finally, if you have not 1 billion but 1 trillion bytes, which actually is not so unreasonable today given how big hard drives are getting, certainly in servers, what is 1 trillion bytes? A terabyte. A terabyte. And some mathematicians with a lot of free time have defined these prefixes even higher than that. But for the most part, we're pretty safe for the next year or so in going only as high as terabytes. Now, with that said, you get your first E1 gag. And if you laugh, well, we'll get to that in a moment. Here is a comic strip from Foxtrot. Do you understand it? We've opened up a whole new world of humor for you now. Sad as that may be. The one thing we haven't done, however, is do anything other than discuss how numbers are represented. Clearly, computers are capable of far more interesting things than addition and subtraction and so forth. Clearly, they can display text, English text, and other languages on the screen. But if at the end of the day, the only thing a computer can understand is zeros and ones, the sort of natural question that follows is, how do you represent not just big numbers like 256 or 4 billion using zeros and ones, but how do you represent the letter A? How do you represent the letter B, right? We totally waved our hand at how do you represent negative numbers. Let's at least give ourselves the benefit of some insight into how letters are stored before moving on. Well, it turns out that that chart captures how letters are represented with a computer. And it's meant to sort of be overwhelming because in not too long from now, it will be quite simple, believe it or not, to understand. Take it for now on faith that computers, if they want to store the letter A, by convention, they simply store, using some number of bits, the number 65. And if you want to store the letter B, Well, you simply store, you being the computer, the value. Take a guess. 66. If you want to store the letter C, 67, and the pattern continues. And in fact, on that chart, that's from a website called ASCIItable.com. The acronym ASCII essentially refers to the set of encodings that computers tend to use to represent letters using numbers. Now, where's the binary? Well, this is just easier for humans to talk in terms of decimals. We say 65, 66, 67, but when a computer really stores the letter A, it's using a byte of bits, and so it's actually storing 65 as a sequence of zeros and ones. But, that was enough of an exercise in binary. Now let's get back to the real world of decimal. So with that said, you can actually represent, for instance, other characters as well. ASCII is a system that quite specifically tells you how, using bytes, 8 bits, to represent letters. So you will hear ASCII referred to as 8-bit ASCII. All this means, which is interesting, is that the total number of characters you can represent using this encoding scheme, if you only have 8 bits at your disposal per character, is how many? 256 total. 256 total. One of those is used up by the letter A, clearly. One of those values is used up by the letter B, and so forth. You can look up in the chart if you want to see how an exclamation point, for instance, is represented. But this is sort of a problem. If you can only represent 256 characters using this standard encoding, not a problem for English. But what about certain Asian languages? What about the global languages? If you take all of the languages in the world and you somehow want to support, like Microsoft certainly does with Windows, any number of languages, ASCII doesn't quite cut it. If you need to be able to store not just Roman characters, A through Z, but other characters as well. ASCII, though, is a nice one because it's easy to talk about, but just know, and if you ever see it in print, we won't spend much time on it, there is an alternative called Unicode. And just take a guess, even using the engineering hats that we've provided you with thus far tonight, what would you do as an engineer if you had more letters in non-English characters that you needed to represent and 8 bits were not enough? Well, what do you do in your computer to represent more letters? You use more than not 1 bit. You use more than 1 byte. So Unicode just uses multiple bytes to represent letters. But let's leave it at that, because what I now need is 8 volunteers. This is perhaps the most socially awkward point of the evening. And I need to offer this caveat. Among the handouts tonight, this is going to sound a lot scarier than it needs to be, but such is what Harvard's lawyers tell us to do. So this poorly photocopied paper is some legalese that Harvard's legal department asks that we have students fill out if, at some point during the semester, you would like to come down here with me and participate in some socially awkward demonstration. The reason being that we do have a camera in the room, which is not only for your benefit, but also for the benefit of our distance education students. Every semester, we have students not only taking the course locally, but also throughout the world, literally beyond the scope of the United States. And this is just a form that says, I am okay with actually appearing on these videos. So with that said, I need 8 volunteers who don't mind being on film. Mind you, this is an even better way of sending an email to mom or dad and saying, hey, not only was I at class today, here's proof that I went to class today. We have 1 volunteer here. That means we just need 7 more. 7 more. Okay, it's got a tough night. All right, 6 more. Come on down. You're going to represent the 128 column. Thank you. And, Ray, do you mind managing these? You have just won the number 64. Can take that? Oh, okay. Ray will ask you for that afterward. 32s, okay, getting more awkward. All right, 16s. 16s, okay, 8s coming up. Oh, we got the 8s coming down. 4s. It's only getting better, right? Number 1, you're waiting for number 1, right? All right, 16s, 4s. Here comes 4s. Put me out of my misery. 2s. And finally, who wants to be number 1? Number 1. Number 1. All right, here we go. All right, number 1. So perhaps needless to say, what we now have here is a byte of volunteers. Ha, 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 right? So the one thing we do need these folks to do, which it looks like they have done already, is line up in decreasing order. So our highest bit is, of course, the 128ths column. Our lowest bit, of course, is the 1s column. And what these folks are about to do is challenge you, those who were not so brave as to volunteer, you get to do the work, is with a challenge of ASCII. What these folks are about to do is represent either a 0 or a 1, a light bulb that's on or that's off. And they're going to represent a 1 by raising their hand, and they're going to represent a 0 by just standing here slightly awkwardly. We're going to do this for 3 rounds, so we're going to spell out 3 different numbers, and each of those numbers is going to represent an ASCII character. The challenge for you, the audience, is to figure out for each of these 3 rounds not only what number these folks, these brave folks, are representing, but also what corresponding letter they are representing. So with that said, on the back of your sheets of paper, volunteers, you have instructions as to what to do in each round. In each round, you're either going to raise your hand to represent a 1 or just stay put representing a 0. Let us begin round 1. So volunteers, if you are a 1, please raise your hand. So we have this hand up. We have 2 hands up. What number is this representing? So that's pretty easy. 66. Turns out we got a little cheat sheet up here. What character are these folks representing, therefore? B. So we have a B. Excellent. We're already up to round 2. Round 2, folks, if you could raise your hand if appropriate. What value are they representing now? So I heard 79. If it's 79, what letter does that represent? An O? Yes? No? 79? All right. Excellent. So we have a B and an O, and we're at our final round, round 3. Folks, if you could raise your hands if appropriate. What letter now? Box. We are not spelling box, no. Close, though. What number first are we representing? It is, in fact, 87, which according to our ASCII chart represents the letter W, which means it's now the time for our volunteers to take their bow. Thank you very much. Oh, no one seems to want their souvenirs. That's fine. Let's go ahead and do the following. We are going to take a 5-minute break, change tapes. If you need to use the restrooms, they're down the hall and down the stairs. There's a little cafe as well. We'll take just a 5-minute break. When we come back, I will give you a sense of exactly what you've gotten yourselves into with this course. Whew. All right. Welcome back to Computer Science E1. So that was a mouthful, sort of a heck of a way to jump into Computer Science E1 and get smacked with all of the bits and bytes and so forth. But hopefully, if you were able to follow along well enough, the takeaway, remember, if nothing else, take comfort. This is how we began here. So we now have the ability to speak in the language that computers do. And you know, to some extent now, how these devices work underneath the hood. So what's the point of all this? Where does it fit in? Well, tonight is our first lecture on hardware, and the goal of this lecture is to build ourselves from the bottom up, from the basic building blocks of computing to, in the latter half of tonight, some of the bigger pieces of hardware with which you're already familiar, at least in name. A computer's motherboard, for instance. A computer's hard drive, for instance, and so forth. So, lest you worry that this is about to be a course in electrical engineering and mathematics, we'll now make use of the fact that you know what binary is, and you know how to represent numbers in this way, and start working our way back up to the juicy stuff that you have actually sitting on your desk or sitting on your laps and your desktops and laptops. So what is this course ultimately all about? What have you gotten yourselves into? Well, for those of you who are taking the course for credit, the expectations are quite simple. To attend or watch all lectures, complete 9 problem sets, take 2 exams, and produce a final project, the latter of which essentially involves developing your very first, or at least very first for this course, a website and your very own personalized domain name. Those of you who are taking this course just for fun, for non-credit, for instance, you are just as welcome and certainly encouraged to partake in precisely these same expectations, though you won't end up with a grade by definition at the course's end, because these problem sets are not so much designed to test how well you were paying attention in lecture, though paying attention in lecture certainly helps with the problem sets. Rather, they're meant to reinforce the material and actually apply a real-world spin to the information that we're talking about in this course, because this course ultimately is about, as the catalog tries to convince, giving you a new vocabulary or giving you a newfound level of comfort, not only with understanding computers and the internet and all things related there too, but for those of you who have the ability physically to attend these classes locally, the course also has a practical component to it in the form of what we call sections and workshops, which we'll come back to in just a moment. So in the course's lecture, we will cover a huge breadth of topics, which are only summarized by the headers above. Tonight and next week are about hardware. Lecture 3 is about software, and believe it or not, in Lecture 3 will be the first of E1's movie nights, where you'll be treated to a little bit of soda pop and popcorn and a film, starring, for those of you familiar with ER, Noah Wiley, as we watch the start through a dramatization. Oh, and Anthony Michael Hall is in this film as well. It is called Pirates of Silicon Valley, and it's a wonderful film, a dramatization of the rise of both Apple Computer and Microsoft. And we'll use that as a proxy for our discussion of software, one component of which, of course, is a computer's operating system. In lectures 4 and 5, we will look at the Internet. How does it work? What can you do on the Internet? What's the difference between the Internet and the World Wide Web? For yet more detail on individual topics that we'll look at in these lectures, I would certainly refer you to our, 16-page syllabus, which lays out in much more detail exactly what we'll do each week. But what that will do is expound on exactly what kinds of juicy content we'll have underneath each of these categories. From Internet, we'll move on to multimedia. We'll talk about video and audio and animation and so forth. For those of you attending locally, we'll have hands-on implementations of GIFs and JPEGs and other such animations and graphics. We'll move on to a couple of lectures on security. Privacy, spyware, worms, viruses. How do you protect yourself against these kinds of threats? What are the threats that you face when turning your computer on literally every day of the week? We'll then turn to website development. You will exit this course, if you haven't the skill already, with the ability to make your own web page. And I don't mean by downloading or paying for some product that allows you to drag a little box here and draw it as exactly as you see fit, but actually get your hands dirty with what's called HTML, the language in which all web pages are written. And we'll similarly build those from the ground up so that you have probably more savvy than a lot of web developers who are only using the higher level applications to develop. If you have no idea what any of that pitch just meant, don't worry, you soon will. Programming. We will spend a week on programming. This is not a course on programming. You will not exit this course programmers, but you will exit this course with a familiarity with what programming is all about, a familiarity with what software developers do, and enough of a taste of programming so that certainly for those of you who find yourself liking this sort of stuff, would have a bit more comfort perhaps proceeding to a programming course like E50A here or at some other university. We'll look at .coms by way of our second of 2 movie nights, by way of a documentary called Startup.com, which if you haven't seen it already, is a wonderful documentary shot by a company called GovWorks.com, who a few years ago in the heyday of the .com era were so perhaps optimistic as to document on camcorders pretty much every day of their corporate lives in the hopes that this would trace their remarkable rise to fame and fortune. Fortunately for us, the viewers, they kept the film rolling as they peaked and then headed on down the other direction, as did so many other .com companies. And it's a wonderful representative depiction of a lot of the hype and a lot of the success and simultaneous failures in that particular era. And laced throughout these lectures will, of course, be other topics such as those enumerated on the syllabus. Lectures. We do have a camera in the room, which means there will be films made available digitally. You can, in addition to attending this course locally, you can also take this course via the Internet. There are certainly, for those of you who are local, an added component, we hope, a dynamism to actually attending locally. But even those local students in the course tend to find the online version of the course and its videos a useful resource and vehicle for review. And we find students will often use the videos that are available online in a few different formats to review lectures that might have gone too quickly, might have been too confusing, lectures they missed, for instance. But as registered students in this course, all of you would have access to high-resolution videos that are being shot tonight that are also synchronized with the types of slides that you see going on up there. But in addition to these files, you also have access to, via this course, the course's podcast. Just as these lectures and other content are made available on audio and video, so is it made available by the more familiar, perhaps, iTunes. And if you follow the appropriate link on the course's website, you'll see, for instance, tonight, a link to Fall 2005's podcast, which are videos of last year's semester of lectures. They don't necessarily have all of the synchronization and so forth of other materials, but similarly, will we soon remove this from 2005 and begin broadcasting Fall 2006. So you will be able to not only partake in the course locally and also take it with you on your computers at home, but you can even, for instance, take it with you on your video, dramatic effect coming, on your video iPod, for instance. Tell you, this is the first computer science course we like to pitch that you can take while jogging, for instance. And there are also audio-only versions of the podcast so that you can actually tune in. What I'll actually do is fast forward through this a little bit and then pass this around. More so than Wooly Willy, I would love for this to make its way back to the front of the room. Let me fast forward to a point here. And we'll pass this around as well. All right, anyhow, what you're seeing here, there we go. So feel free to pass that around. So, in addition to the course's lectures, there is a practical component to the course, which includes, as we said, books. Okay, got this out of order. So the course has a number of recommended books. So no books are required, and God forbid you ever be expected to buy a stack of books that is this tall. These books here are the course's recommended texts. What we've done and what we've found useful over the past few years is that because this course has certainly at least two different types of students, those who are particularly savvy with computers, but who are looking perhaps to fill in some blanks in their knowledge and get a bit more savvy with some of the more technical material. And then we've had students who certainly have never used a computer before, or if they have, they're scared to death of it, certainly if something goes wrong with that computer. So we try to mitigate these sort of dueling interests in the course by way of two sets of books. And if you look at the books section in the syllabus, you'll see that we have one set of books, set one, for quote-unquote true beginners, and then another set of books for students who are more savvy. The goal of these two sets of books is that though both of them contain and recommend, for instance, this book, which, if anything, is sort of the course's textbook, they also contain different supplementary material. So for instance, whereas in set one for true beginners, there's this nice Teach Yourself Visually book that talks about computers and computer hardware, we have a similarly visual but much more technical version in the second set of books for those of you who want a bit more of a challenge and want a bit more technical material to look through at your leisure. There is nonetheless so much material in this course that you are not required, nor is it even necessary to follow along by way of these books, but they are on reserve in Grossman Library, which is the Extension School's library. I will say that though they should be available in the coop, perhaps I should say this off film, they are available much less expensively online. So what we have linked on the course's syllabus are links, I think, to Amazon.com, and not even just Amazon, but the third-party sellers. Honestly, the books, in my opinion, though this is valuable, is not necessarily worth the whatever $100 that it costs. So look for instance, discounts online. I think it's a great book, but I would be remiss in suggesting you go out and pay full price for these kinds of texts. But they should be invaluable resources, or certainly good reading if you like this sort of material. And look to the syllabus for more detail. We leave it to you to decide which, if either, of the sets of books you might like to invest in. Sections. Those of you who are taking this course locally have the opportunity to work not only conceptually with computers and the internet by way of lectures, but in a more intimate setting with the teaching fellows in what we call sections, aka recitations. It's in sections, which are 2-hour classes in addition to lecture, that you will literally sit down with the computer in front of you, be it one that's about to be dissected or an actual operational computer, and it's in section that will partake in such activities as these. The first section, and these do not start until next Wednesday. There's no section tonight or this weekend, but starting next Wednesday, as we'll discuss in a moment, you will have an opportunity with the teaching fellows at your side to take apart a computer. And though we like the computers to work after the fact, that never actually seems to be the case. So every year we go recruiting for new hardware. So you'll start to open up a case like this and start pulling parts out, ideally gently, but in a way with the teaching fellows by your side that it's exploratory, pointing out different pieces of hardware, what goes where. If you want to upgrade your computer, where do you put what? And that would be, for instance, the focus of our second section. Yeah?
If, for example, you have another class after this and you also have a class that happens to meet on Saturday,
Mm-hmm.
will the sections be videotaped?
A good question. Will sections be videotaped? Most of them will not be. Because they are hands-on, they don't particularly lend themselves to videography, if only because watching other people have fun with computers and the internet for 2 hours tends not to make for good TV. Some of them will be recorded, perhaps via audio, if conducive to that. But unfortunately, it's simply a real-world constraint. But you can chat with us after if you'd like to discuss further. Other questions? Well, what are some of these other hands-on activities? Exploring the internet. Again, the course caters to all types of students as best as we can, and certainly lays throughout some of these topics, even if they might sound fairly easy on first glance to some of you, and even if they might sound scary to others of you, we try to balance both in the classroom. Exploring the internet, finding out what kinds of resources are there, treasure hunting, learning to search better. Finding information on the internet is perhaps one of the hardest and yet most obvious uses of the internet. Well, how do you do more advanced searches, be it via Google? What resources are available for you to search? That's one of the foci for our treasure hunting section. After that, how do you build and configure your own network, your own home network, aka a LAN or WLAN, a wireless LAN? In other words, you would exit that section knowing what hardware you need to buy, what wires you need to plug in to actually get your own home, apartment, or so forth up and running with its own network, cable modem, DSL modem, or so forth. After that, we would look at multimedia. You will design your own graphics in section using an industry standard program called Photoshop. And I should say that though this course does not teach you how to use programs, this is not a course on how to use Microsoft Word. This is not a course on how to use Microsoft Excel. When we get to a point like how to develop multimedia, we do occasionally pull off the shelf the most popular programs with which to explore these very types of topics. Out of that will come one of the course's problem sets, in fact. What you will be tasked with in a future problem set is to design, if you wish, for extra credit, a candidate design for Fall 2006's Mousepad. If you haven't looked at the course's website just yet, you'll notice at the left there's a link to Mousepads. As sort of a fun project every semester, we challenge students to come up with a design using their newfound multimedia skills and a proposal for a Mousepad. Toward the end of the semester, we, the students, would then vote on your favorite Mousepad design. And at the course's final lecture, we would reveal to you the winner, and each of you would go home the lucky recipient, hopefully of an A, but if nothing else, of a Mousepad such as this. And this was in the year that the Matrix was popular. This was the winning design that year. The other designs are online as well. Building websites with XHTML. You will exit this course knowing how to develop web pages using the standard languages thereof. Enhancing websites with cascading style sheets, something very much related to HTML or XHTML. And programming. We'll introduce you to programming by way of a fun programming environment, very graphical and sound and animation oriented, developed by MIT's Media Lab. These sections will be led by the course's 3 teaching fellows, who I'd like to come up for just a moment if they would and say hello. In a moment, after these folks say hello, we'll address exactly how you go about interacting with these folks and when and where. But if you all would like to say a quick hello and standing next to me so that you're on microphone, that would be great.
Hi, my name is Ray. Some of my hobbies include movies, video games, and comic books.
And Ray is the course's head teaching fellow, which means that he handles a lot of the administrative and managerial tasks for the course, particularly assigning students to section, handling logistics such as that. So certainly if you find me intimidating or annoying, you can certainly speak with Ray about details such as that. Next we have...
Hi everyone, I'm Dan. I currently work at MIT for MIT's IS&T department here. So hope to see you in the section.
Okay, fantastic. And Eugenia.
Hi, I'm Eugenia, and I just started this evening, so I'm as bewildered as the rest of you.
Oh, it's fantastic. We got a crack team here. Okay, well, thank you. let me draw your attention to one of tonight's handouts, which is this sectioning form. Officially, sections are optional. Those of you who are physically able, though, to come to campus are strongly encouraged to take advantage of these, beginning immediately with the start of the semester. Again, these are meant to be hands-on opportunities. We offer 2 sections during the week, both of which are essentially identical, and the teaching fellows will rotate over the months as to who is teaching which section and so forth. So though you'll be assigned to a specific day or time, the teachers with whom you'll interact will rotate. What we ask you on this form, and if you would please leave this form with us on your way out, is your preferences for these sections. And certainly, as we say, if your attendance is not possible at one night because of some other commitment, you're certainly welcome to go to the other night. For convenience sake and based on historical preferences, we offer one of these sections starting next Wednesday, right after lecture, so that you can just deal with one commute to Cambridge during the week, but also for those of you who work and find going to class not only from 5:30 to 7:30, but 7:30 to 9:30 as well, a bit arduous, there's also a Saturday afternoon option as well. In addition to these sections, there's another aspect of hands-on interaction in this course. These are called workshops. Workshops are slated per the syllabus for various Saturday and Sunday afternoons during the semester, and these are meant to be additional topical sessions that are, in some sense, tangential to the course. There's only so much we can officially bite off and actually hope that students will absorb. Workshops are meant to explore related, fun, sometimes more technical knowledge in more depth. However, the first workshop is designed for the other end of the spectrum. If there are any of you in the room or feeling particularly uncomfortable with computers and the internet, dare say have never used one before, the first workshop is designed to help level the playing field, in a sense, so that if you're unsure as to how you would find the course's website, how you would get a handout off the course's website, how you would watch a video, how you would turn on a computer to access the course's website, that's what this first workshop is designed to do. It's really for the neophytes among the students. The specifics as to time and location are available either in the syllabus or online, and we'll certainly announce it each week. After that, we have workshops focusing on mastering Windows, doing more than just double-clicking, but actually configuring your Windows box, fixing problems, doing the same with Mac OS. 4 weeks or so from now, we will also lead a field trip to MIT's Swap Fest, which is a tag sale, a flea market of sorts for really old, yet really cool, from some perspectives, computer stuff and electronic stuff. So we'll make a short but fun afternoon out of that and head over to MIT around lunchtime for that. More on that in the future. Tour of a NOC. You will have the opportunity to tour the inside of Harvard University's NOC, Network Operations Center, and get a peek at what exactly goes on behind the scenes of a fairly large network operation. Building a PC, a workshop that focuses not just on upgrading a PC, but in actually buying individual parts, putting them all together, and voila, you hopefully have a working brand new PC that's not bought from Dell, but that's maybe bought from various stores online, and you yourselves might assemble it. What we'll do in this Master the Internet session, for those of you who are feeling pretty confident in your newfound savvy with computers and the internet, we have actually engaged in a partnership with Harvard Extension's Institute for Learning and Retirement. So you, the students, will have an opportunity, if you choose in this workshop, to become teachers and actually work with some local retirees and essentially work with them hands-on in a computer lab on material very similar in spirit to what we'll focus on in the earliest weeks of this course. Beyond that, Ray, quite the aficionado of games, so we'd be remiss in not devoting a workshop to computer games and fun thereof. Digital photos, digital videos, enhancing websites with a technology called Flash, enhancing them with a language called JavaScript. All of those will be slotted for upcoming workshops, some of which will be filmed either on video or at least audio. The course has 9 problem sets. You will typically have roughly 2 to 3 weeks for each of these problem sets. There's no homework distributed tonight. There's nothing due next week. The first problem set per the syllabus will be released next Wednesday. And what they are meant to do, again, is not so much test understanding and not so much test your ability to pay attention during 2-hour lectures on technical material, but rather reinforce things. In fact, one of these homework assignments will actually task you with or hand to you some virtual dollars with which to go shopping at a local computer store. We can only do this once a year because the salespeople are never quite thrilled to learn that the students are coming in tasked with buying $2,000 worth of equipment with funny money. So we can't do this too often, but that will be among this semester's challenges. But more on that in the future. Final project. For those of you those of you enrolled for credit, certainly are tasked with a final project, which essentially, and this is fun even for those of you just doing the course for fun, to buy your own domain name, for instance, davidmalan.com, though, sorry, that one's taken, and actually hosting it somewhere, and we'll help with this, and actually developing your own website and really then your own presence on the web. Whether you want to make it personal, whether you want to make it entrepreneurial, whether you want to just make it silly, that will be entirely up to you, but you will know by course's end how to not only develop a website, but actually get it online at yourfirstname.com, for instance. So more on that in the future. Grades, and again, I'll defer to the syllabus for more detail, will be allocated as such. The course's website, however, will hopefully be an invaluable resource, if only because we make everything that happens in this class available via its website. Not just the lectures and the videos thereof, but any handout that's ever given out in lecture is immediately posted on the course's website in PDF format. So you can download it, print it, review it, and so forth. Old exams, for instance, if you want to get a sense of what kind of material the course really covers or what the course's exams are like, you can take a look at Fall 2005's. On here as well are, of course, problem sets, contact information for us, as well as a new project which we've begun this year, which is our Videos of the Week. So what we found in podcasting the course last year is that it was well received overall, certainly by local students and those more distant. However, when you want to learn a little something about hardware, you don't necessarily want to sink 2 hours of your evening listening to me talk about hardware. So what these Videos of the Week are designed to do are to be more bite-sized. And they'll be produced by the teaching fellows, up to 4 each week, that will be released via the website throughout the semester. And they will be on 5 to 15 or so minute segments on very specific material. For instance, how to put RAM in your computer. The teaching fellows on film would lead you through that process, for instance. So in just a few days' time, the first 4 videos will be on display, and every week thereafter, we'll release another set of those as well. They are called Videos of the Week, so they are under the Videos of the Week link right there. The course has as well, let me get this right, the ability for you to access your grades via the course's website. If you would like the ability, not only to get feedback, obviously, from the staff, but to just check up on your grades, exam scores, problem set scores via the course's website, we just ask that you do this to comply with FERPA and so forth. But what you will also get during each lecture is this yellow piece of paper, which some of you were so expertly reading off of before. This is tonight's list of jargon. So there is a huge amount of information in this course. For instance, and I'm going to fast forward for a moment, this appears in the course's syllabus. And this is a photograph from a few years ago of a hack at MIT. And some industrious students connected a working fire hydrant to a water fountain and then placed a sign up at top right saying, getting an education from MIT is like drinking from a fire hydrant. The analogy being that you get hit with so much information that you can't possibly swallow it all. That is precisely the design of this course. You are certainly not expected, come lecture's end tonight, to be able to regurgitate certainly everything we've done, but that it's hit you, and that you've heard it, and that you'll know at course's end where to go for more information, not just our handouts, but online resources. That's the course's aim, to take away the fear factor, to level the playing field in terms of savvy with computers and the internet, and generally give you a sense of empowerment. And I don't even mean to use big hyperbole here, but to really give you a level of comfort that perhaps you haven't entered the course with, in addition to technical savvy. Taking notes is not fun. It is also a distraction to some extent, certainly when the course emphasizes things like acronyms and buzzwords and pieces of jargon. So at every week's lecture, we will hand out to you a yellow sheet of paper like this that essentially is a cheat sheet of definitions. It's not so interesting to memorize these terms, but if I use them, like a byte, and you sort of zoned out a few minutes ago, or you've been hit with so much other information, the byte got pushed out the other end, well, this is a nice little cheat sheet to have, not only for review, but also during lecture as well. And in fact, what the teaching fellows will do during each lecture is take notes of their own, scribe notes of sorts, that will also be placed online on the course's website, so as to potentially free you as well from the inclination to take incredibly verbose notes of your own. The goal is to more in these lectures engage in a conversation, ask questions, answer questions, and so forth, and not spend the entire time with your heads down on the paper. So all of these resources will be in place for you to make use of, and all of them will certainly be accessible via the course's website. Let me pause for a moment and ask if there are any questions. Yes?
If you're doing distance education, is there a way to hand in the problem section?
Yes, if you are partaking in distance education or simply you can't make it to lecture 1 week and to hand in, for instance, a problem set, all homeworks will actually be submitted eventually via the course's website. We'll talk about that more next week, but you will do it electronically. Yes. Other questions? Yes?
If you're taking the class for credit and you have to miss a lecture but you can watch it online, is that still acceptable?
Absolutely. If you have to miss a lecture for whatever reason, you are more than welcome to make it up by simply watching or listening to the lecture via any of the available online means. Other questions? Well, what could possibly be the relevance of these two guys here? So on the course's website and in the syllabus as well is a reference to staff's picks. So a fun way of acquainting folks with computers and the internet, of course, is to kick back, not necessarily with soda and popcorn here, but soda and popcorn at home. What we have then listed on the course's website are a bunch of movies that the staff has selected and proposed as being rather apropos for students learning about computers and the internet. And what we will do on each problem set is offer you an opportunity to rent or borrow one of these films, write a review of sorts, a thumbs up, thumbs down sort of review. The syllabus offers more detail, and if you email that to us, right around the time you submit the problem set, you will have the opportunity to receive a bit of extra credit. So not only is it a fun way or a fun excuse to say, I gotta watch a movie tonight, it's also a way to help you feel a bit better if, for instance, one of your recent problem set scores was not as high as you might have liked. So you may recognize a few of these. All of them have a computer or internet spin to them. More on that, though, in the syllabus. And if you'd like to reach us, of course, via email, the whole staff reads that particular address, though you're welcome to email us individually. And finally, this cardboard box, which every week has tended to take a different form depending on what box we find lying around, is the Not Dumb question box. So it's one thing to be able to ask questions. It's another to be comfortable asking questions, especially if you feel, as many students often do, that everyone behind you and in front of you and to the side of you knows more than you do. And perhaps that only was reinforced by our little example before if the person to the left of you and to the right of you had better answers in your binary questions. But what we often do during the week, during each lecture, is we put a box, not unlike this one, called the Not Dumb question box. And this is an opportunity, somewhat semi-anonymously, to crumple up a piece of paper with a burning question that you might have, but you're just too ashamed to ask it, or you don't want it to be assigned to your name. Drop it in the box, and I'll do my best to remember to look in the box and see around middle of the lecture if there are any questions related thereto. This is, we like to say too, we for years also had a dumb question box, but we try only to emphasize the one here. And actually we've gone, does that make sense now? So that didn't go over well that year. So what we've also done this year is gone digital. And as you'll see on the course's website, there is a link not to a physical cardboard box, but to notdumbquestions.com, which is simply the digital incarnation of this. So similarly, if you would like pseudo-anonymously to pull up the course's website and link to, for instance, up top here, ask a question, you'll be whisked away to our own website. It's not some random site out there. Our own website, notdumbquestions.com, where you can pose fairly anonymously a question, and we will do our best to offer you a good answer via that website as well. So you can just check up on it remotely. With that said, that's about everything that encompasses the course's logistics. Are there any questions? Anything at all? All right, so tonight is about how computers work and looking at the inside of a computer and looking underneath the hood of a computer exactly how things work. What we'll do next week, incidentally, just to give you a teaser, is to work even above this, talking about some of the larger pieces of computer equipment, be it monitors or printers or hard drives or other such devices. But tonight we're going to focus more on the tiny stuff, the stuff that you may have heard is inside your computer, but you certainly haven't taken it out yourself. You certainly wouldn't know perhaps where to find it, even if you were told, go find me the CPU. You know it's in there, but as to where, that might be another question unto itself. Well, every one of you who has a computer, be it at home or work, has a CPU inside of it. What, so far as you know, is a computer's CPU? Yeah, it's brain. It's the brain of the computer. It is the piece of hardware inside of it that does the computer's thinking. For the most part, this involves a whole bunch of mathematics and stuff, but essentially this is the brain of the computer. Anything the computer does, it's doing it, and it's doing it at a speed consistent with its computer CPU. And actually, I just mentioned speed. What units is a CPU's speed measured in? Megahertz or gigahertz. So if you've ever been asked how fast is your computer, or you've ever been told how fast your computer is, you've probably been told it's 800 megahertz, or 1.6 gigahertz, or 2 gigahertz. Well, there are these prefixes again. Well, what do we mean by giga? What did we mean by giga? Billion. What's a hertz? Well, hertz is just a sort of a electronics measure, something per second. So if you say that your computer is operating at 2 gigahertz, that means it's doing 2, or can do, 2 billion things per second. Well, what can it do per second? Well, you probably know that inside of a computer is some kind of clock or a little crystal. And it's that crystal's speed of oscillation that drives the computer speed. All this just means is that there is something in your computer clicking inaudibly 2 billion times per second if your computer's CPU runs at 2 gigahertz. On every stroke of that clock, your computer can do something. And what can it do? It can add 2 numbers together. It can display something, for instance, on the screen. It can print something out to the printer. It's a bit of a simplification. Usually what it can do are more basic building blocks, but the idea is the same. Every time this clock strikes something, your computer can do something. Which is to say, if you have a faster CPU, something that operates not at 800 megahertz, million hertz, but 2 gigahertz, well, that just means your computer, in effect, is more than twice as fast. It can do the same work, but it can do it faster than the older computer because it's clicking, it's chirping away more than twice as quickly. Well, what's an example of a CPU? Like, what kind of CPU do most of you have? Pentium of some sort. So most computers, at least that consumers tend to buy, have one of Intel's CPUs. A Pentium 2, a Pentium 3, a Pentium 4. There are other companies, AMD makes compatible CPUs. If you have a Macintosh, you either have a PowerPC chip, or these days you actually have an Intel chip, perhaps, and the newest of Macs. Those are just the different manufacturers, and actually the one CPU's picture that I'll draw your attention to is actually the one on bottom right here. So this was sort of a cute Apple marketing campaign years ago. You have a snail there carrying the Pentium 2 CPU on its back. The implication being that it worked much more slowly than the equivalent Macintosh CPU at the time. What I will do now, and I see the iPod hasn't made its way back to the front yet, is pass around in addition a few CPUs. Essentially, the 2 forms in which CPUs come today are either, as you see there on top of the snail, this large cartridge, sort of like an old Nintendo cartridge kind of thing that just plugs into the motherboard. Most of this Pentium 2 that I'll pass around is not the CPU itself, but it's this big metal thing. What in the world is that? Yeah, it's called a heatsink. So CPUs get really hot, and the faster your computer works, the hotter it gets. And this is a problem because if computers get too hot, things can burn out, and you can literally damage your computer. You, the user, can't usually do this, but if your fans break inside your computer, or if you do what's called overclocking, that is turning a virtual knob saying, make my computer that should operate at 2 gigahertz, try to operate at 2.4 gigahertz, well, sometimes you can fry your own CPU in that way. So things like this, in addition to fans, heat sinks, are just pieces of metal with lots of surface area so that a lot of air can blow through it and actually dissipate some of the heat. So I'll pass this around. Another type of CPU that's popular is not this cartridge, but increasingly again today are these square-like CPUs that have a lot of gold pins. They're not normally as bent as they are in E1's hardware here, but essentially these two just get plopped right inside of a computer, and they too tend to have heat sinks on top of them. But the CPU is really just the small chip in the middle there. All of these pins are just there to connect to, for instance, wires inside of the computer. In fact, to what does a CPU connect inside of your computer? Yeah, this thing called the motherboard. So whereas a CPU is the brains, in effect, of your computer, a CPU might be said to be the central artery system. This is perhaps the biggest thing inside of most computers, and it's big because so much stuff connects to it. Pretty much anything inside your computer ultimately connects to or passes through this motherboard. And as such, it's the central artery system. Any information that's going, for instance, from your keyboard into the motherboard will eventually go back to, for instance, your printer or to your monitor. So all of that information gets routed through here, and you can see that on this motherboard is in fact a CPU because on top of it is a heatsink. And for tonight's purposes, don't pry things off these motherboards just yet. We'll have the chance to do that in section, but here too is another motherboard that doesn't have a CPU, but you can see the holes into which one of those square ones might fit. So we'll pass these around as well. We have next just this depiction. What is it that is on a motherboard? Well, if it's the central artery system through which most data and information flows, to which most devices connect, what is physically on your motherboard? Well, ports, that is holes for your CPU. Well, what else is inside of a computer? Sorry? So a battery, so that it always retains, for instance, the current time, even when the computer is off. What else is inside of a computer? So a fan might connect to the CPU, drives, hard drives, floppy drives, and so forth. All of those connect to the computer in some manner. This, for instance, is a ribbon cable. It's called an IDE cable. We'll come back to IDE and ATA and SATA next week. But this is the type of cable that hard drives use to connect from themselves to a computer's motherboard. And notice for now, it's just a very cheap device, but there are a number of holes there that will fit into the hard drives that we'll pass around next week, as well as tonight. This is really a teaser. We won't spend time tonight talking about hard drives. Notice, though, that inside of a hard drive, for tonight's purposes, are essentially a bunch of floppy disks, just like the ones you saw, except the hard drives are stronger, they spin faster, and they store more magnetic particles, and there are often multiple platters, as they're called. And what you have here is sort of a before hard drive and then an after hard drive. After meaning after E1 took a screwdriver to it and opened it up. So we'll pass these around as well, but we'll spend more time on these next week in our second hardware lecture. But you'll get a glimpse of what is inside. Finally, gentlemen said drives are connected to the motherboard. Here's a floppy drive. So the disks that we destroyed would normally go into this thing. There's not too much going on here, but you can at least see the circuit board, which is like a mini motherboard that's connected to this particular floppy drive. So what you see above here is sort of a representative picture of a motherboard where, based on our discussion thus far and what I've held up, do you think on this motherboard the CPU goes? Yeah, middle right. So fortunately, there's a bit of a cheat sheet there. The processor, which makes sense because what does CPU stand for? Central Processing Unit. And incidentally, in this course, acronyms, often, who cares what they stand for? It's often useful because it explains what it is. But this, again, will not be a course in which we say memorize the following list of 200 acronyms and tell us what they mean. There's little value in that. So again, when we start saying things like CPU and you're not sure what a CPU is, well, fortunately, on page 2, we see that it means Central Processing Unit, the brains of a computer. So again, rely on your cheat sheets if need be. What about a computer's memory? Well, you've probably sometimes been asked, or maybe you've asked someone else, how much memory does my computer have? Well, there's two types of memory in a computer, at least two. One is your hard disk space, right? That's where you store all of your information, all of your files on your hard drive. Well, we'll get back to that next week. But hard drives, even though they're huge these days, and even though those platters spin very quickly, they're relatively slow. And you don't want to, for instance, your computer to only use bits that are stored on your hard drive. You want them to be stored, these bits, not just on a hard drive, but in something called RAM. So every computer that you're probably familiar with has what's called RAM inside of it. And really, when someone asks you how much memory does your computer have, what that question should mean is how much RAM does your computer have. You don't say how much memory do you have, meaning your hard disk, you would instead say, how much storage space do you have, just to make the distinction. I'll pass these around, and for those of you who have the motherboards coming to you or in your hands, notice that the RAM in a typical motherboard just goes into these horizontal slots. In this example, at top right, on both of the motherboards going around, you can find similar slots. Those little RAM chips fit right inside there. But your computer has other slots often. And for those of you local in our section on dissecting a computer, we'll spend more time with this hands-on stuff and explain more of the details of the computer. But you also have on a motherboard, in most any computer today, other slots, such as these at left. How many of you have ever had to install what's called an expansion card in your computer? So a few of you, maybe half a dozen. These days, there's a huge amount of features built into motherboards. Your motherboards out of the box already have a sound port on them. That is, you can plug in speakers or a microphone. They already have a network jack. So if you want to connect to your cable modem, there's probably a jack on the back of your computer already. If you want to connect a printer, there's probably a port, a USB port on the back of your computer to which you can connect. For a while, though, if you ever wanted to have a modem in your computer or a network connection in your computer, you would need to buy what are called expansion cards, which are just often green circuit boards with special connectors that slide into slots on the motherboard, such as these here. These days, so much more is crammed into the motherboard that you don't often need to go out and buy an expansion card. But just so that you've seen the jargon before, even though it is becoming somewhat decreasingly relevant, at least for typical users and their needs, the types of slots you usually see in a computer today are PCI, just the standard that describes them, PCIe, which is just a faster version. The E means express. And you see something called AGP. So we can spend more time on this either in Q&A form or in sections and workshops. But for instance, those of you who might be particularly gung-ho about building a computer, and you want a really souped-up gaming computer, for instance. Well, among the expenses in a really good gaming computer is to invest in a really good video card. That is a little circuit board that can cost between $10 and $200 or $300 that plugs into your motherboard into one of these so-called expansion slots. It sticks out the back of your computer, right? So even in this computer, you can see that there are some things jutting out. For instance, this right here is a video card. Now this happens to be a PCI card, so it's an older, cheaper card. But notice that on the back of this, if you've ever looked at the back of your computer, there's a blue connector, a VGA connector. That just means this is where you connect what? Your monitor. And in fact, the best homework you can do for yourself tonight, perhaps, if you've never done so, and if the idea of it scares the heck out of you, is go home tonight, take the back of your computer, or better yet, a roommate or family member's computer, and unplug every cable from the back of the computer without memorizing where it should go. And then, literally, it's sort of an exercise in matching shapes and colors. Then, give yourself the experience of actually plugging everything back in, though it might be somewhat daunting on first thought, at least for some of you. The fact of the matter is, so many computers these days are literally encoded not only with proper shapes, but with colors. Like, it really doesn't get any easier than that. But we do find that in this course, there are certainly some among you who might be, if you get a new computer out of the box, now what do I do? It's actually a good exercise. And in fact, we try, just because even in the first lecture we throw such a fire hydrant at you, we try actually to be a bit disarming. And it's probably a good moment to take pause here and just offer this bit of instruction for those of you feeling a bit overwhelmed. Wait. That's going to be anticlimactic with the music in the background. Let's try this again.
This is the on-off switch. On some computers, it may be found on the back or side. If you use this switch to reboot your computer, you should wait 10 seconds after turning it off before you turn it on again. This will help your PC keep everything clear.
Okay. How are we with that? Because we can pause. We got a whole assortment of these things. In fact, why don't we actually make things slightly more technical? And because we dissected a floppy disk before, let's take a look at this, which better than I can explain verbally gives you a sense of how things work inside.
The floppy drive you see here works with 3.5-inch floppy disks. They're the type most often used to carry new programs, save data, or to move files from one PC to another. The part of the disk we see is actually just the hard plastic shell. The working disk, which is inside, is protected by a sliding metal shutter. This thin inner disk, called the cookie, is coated not with chocolate chips, but with a very thin layer of magnetic material. When you slip the disk into your floppy drive, a system of levers pushes back the metal shutter. The levers also pinch two read-write heads closer so they almost touch the cookie. A motor at the base of the drive spins the cookie based on commands from your PC. The PC also signals another motor to move the read-write heads back and forth over the surface of the disk, so they can read or write data. Before your PC writes data, your drive first checks the Write Protect tab in the corner of the floppy disk. If it is open, light from a tiny diode shines through and strikes a diode on the other side. This diode then says to your PC, "Don't write on this disk." But if the tab is closed, no light gets through, and the PC knows it's okay to write data.
So that was very much a mechanical insight into a floppy drive. Let's now try to tie together the earliest discussion we had as to how data is stored magnetically in terms of the alignment of particles, and take one closer look at how data is actually being stored by that reading head that was moving back and forth as the floppy spun inside of a floppy disk.
To write data onto a floppy disk, your PC tells the drive to send tiny pulses of electricity through the heads. The pulses make the heads act like little electromagnets. Each head creates a magnetic field that reaches the surface of the disk. Remember the magnetic coating on the cookie? The magnetic field alters the tiny particles in this coating. If current runs through the heads one way, the particles are arranged with their north and south poles in one direction. But if current flows through the heads the opposite way, the polarity reverses. To read data from a disk, the read-write heads move into the same position over the cookie, but this time the process is reversed. The cookie particles create a magnetic field in the coils of wire, and this creates a current in the read-write heads. The disk drive detects this flow of electricity and passes it onto the PC. The PC translates the back and forth current changes into a series of ones and zeros, the binary language of computer data.
So let's try to put some of this now into more of a context. What we now have here on the leftmost screen is the projection of this little video camera here. So we have here a PC. This is an older Pentium 2 computer. This is an older Pentium 3 computer. We'll fix that on the tape. That has a lot of the hardware that we've been looking at or talking about just now. And again, you can do more of this hands-on if you would like in section. But what we have here is, if you've never seen it, here we have Ray. And if you've never seen it before, what we have here is effectively the inside of a computer. And it's not optimal viewing circumstances with this tiny camera, but notice if I point here, this is a huge piece of metal. What is this thing then? Yeah, that's the heatsink that's attached to the CPU. And it's tough to see, but this computer has one of the older cartridge styles. This is a bad vantage point, but this black thing here that's attached to this big metal thing is just the CPU in this computer. And if we push the right levers inside of the computer, that thing will pop right out. And you'll see exactly what we've been passing around here. If we move these cables aside, you'll see a couple of these long chips of sorts. If I push the levers, this will put it into the context with which we're already familiar. And this thing here is an example, of course, of memory, specifically RAM. So if you were actually to buy more RAM for your computer and actually upgrade your computer's RAM, what you'd be doing is not taking one of these out necessarily, but buying and putting one of these back in. And depending on the computer, sometimes you install these individually, sometimes you have to install them in pairs. You simply have to look at your manual or, for instance, at some online specification as to what you need. And sometimes you do, in fact, need to throw old RAM away or give it to someone else, because notice, how many slots does this computer seem to have? Yeah, just 3. So there is a limit. So similarly in your user's manual or in some online spec would be specification of how much RAM total your computer can have, and in the form of how many of these DIMMs, as they tend to be called, dual inline memory modules, DIMMs. Over here we had the former location of that video card. So this brown thing here is just the PCI slot. that we discussed earlier. And if we look at the back of the computer here, notice that this is where the backs of expansion cards tend to stick out. And this is where the ports, that is the connectors themselves, would typically reveal themselves. Yeah, question?
What's the biggest RAM chip
What?
you could buy?
What is the biggest RAM chip you can buy? The biggest DIMM or so forth these days is probably, I don't know exactly. I know in my computer I have 2 1 gigabyte DIMMs. I suspect you could get 2 gigabyte DIMMs, but I've not had the occasion to even look for it. And for servers, even larger perhaps these days. But I can take a look and try to answer that next week as well. Other questions on the innards of this computer here? Well, where does the actual turning on of this computer come into place? Well, those of you who have a PC that doesn't instead have some pretty welcome to Gateway or welcome to Dell splash screen that comes up, you've probably seen a screen more like this. Yes? No? Not necessarily quite like this one, but if you turn on a PC, before you see the pretty Windows logo, what you usually see is a bit more esoteric information. Sometimes the computer will count up exactly how much RAM is in the computer. This is the point at which your computer will check, is the keyboard attached? In fact, as a second optional homework assignment, what I would challenge you to do if you have PCs is when you've disconnected everything from your computer, or your friend's computer, plug everything back in except for the keyboard. And most likely, if your computer is set up in a standard way, when you then try to boot it up, you'll see not necessarily the pretty Dell logo, but at some point you'll see a more black and white screen like this and an error message saying keyboard not present. And sort of the irony is, and this is literally the case on many older computers, you will get messages sometimes saying, keyboard not found, press F1 to continue. Doesn't quite work, but such were the engineers who actually developed these things. But long story short, what's happening when you first turn on your computer is what's called the power on self-test, aka post. This is just one of the things your computer does, and it often reports to you in sometimes arcane language what it's doing, but it's just the process of checking, hey, do I have a mouse? Hey, do I have a keyboard? And once it's certain that it has all the basics in place, that is, everything's connected, then it says, all right, Windows or Mac OS, take over from here. And that's when you would then see the operating system start to kick in. In fact, what is loading the very first time you turn on your computer is something from what's called ROM. So inside of your computer, so far as tonight's purposes go, are a few types of memory. One is RAM, and we'll come back to this next week as well, but one is also ROM. RAM, incidentally, is random access memory. ROM, though, is read-only memory. Read-only memory tends to store what's called a computer's BIOS, basic input-output system. Literally built into the insides of a computer are a whole bunch of chips. For instance, you can see here a black chip that's a little illegible, but it's made by Intel. There's other such chips over there. One of those chips represents the computer's ROM, which is a chunk of memory that, as the name implied, is read-only. It can never be changed. Small oversimplification there. But inside the BIOS is just the basic functionality of any computer. How to display something on the screen. How to get input from a mouse. How to get input from a keyboard. In short, even if you have no hard drive in your computer, you haven't even installed Windows onto your brand new computer yet, your computer does have a BIOS, which means if you throw the switch, you will see something on the screen. Macintosh users, you don't see such esoteric screens as this, but you'll often see what is described as the Happy Mac face, or God forbid, the sad Mac face, which was often a very bad thing, and it meant that something had failed in terms of hardware. Well, that too was just an incarnation of a basic input-output system, which means that built into every computer in the form of ROM, which is somehow permanently attached to the motherboard, is just a basic understanding of all of the computer's inner components. And it's essentially this process. When you turn on your computer, the BIOS loads and does its thing, checks if everything's connected like the keyboard, and then it effectively passes control off to your operating system. And that's when you then see the screen of like Windows or Mac OS with which you're familiar. And incidentally, and you can do this in section locally, among the things you can do with your BIOS is tweak some fairly arcane settings. Those of you who are a bit more gregarious when it comes to playing with your computer, if you ever want to try overclocking your computer, that is turning a virtual knob so that your CPU tries to tick faster than it should, well, you would often do that using the BIOS's interface by hitting, for instance, F12 when the computer is first starting up, or hitting the delete key just when the computer is starting up. So another exercise, if you so choose, for PC users. Macintosh, Apple has long hid this kind of functionality from people, but in PCs, watch on your screen, or if you don't see any instructions as to what key to hit, honestly, what I often do, even on my own machine, because I never remember what key it is, hit often F1, delete, and maybe F12, and just like this, and you'll probably see a screen like that. You don't necessarily want to change things, even though you can't really do a huge amount of damage with most computers, but you'll see things like the ability to change the clock. The BIOS is so basic as to store your computer's time, in effect, and a bunch of other settings as well. And if you're ever experiencing particularly challenging problems, for instance, hardware problems, you buy a new printer, you connect it, and for some reason Windows just doesn't recognize it, and tech support has no idea what's going wrong, well, sometimes such problems can be resolved by tweaking certain more advanced settings in your, or by way of your computer's BIOS. And in fact, one of this week's videos of the week that will soon be released actually has Ray exploring on camera precisely these kinds of settings. RAM, again, comes in the form of DIMMs or other types of memory modules. These are just a depiction of some popular types of memory. But there is one last piece of memory that we want to address tonight, if only because when you go out to buy a computer and you read the specifications of some computer off a tag at Best Buy or CompUSA or the like, you'll see numbers mentioning these kinds of hardware. Well, we talked about CPUs tonight. We've talked about RAM tonight. We've talked about ROM and so forth. But how does all of this relate? Right? Let's conclude by tying these things together. Well, your CPU is the brain of your computer. Your hard drive, as we'll come back to next week, is the type of memory that stores permanently all of your programs, all of your documents. And by permanently, I mean when you pull the cord or turn it off, the data stays there, and that's a good thing. And the units, of course, as you said yourself earlier, are on the order of, say, a 20 gigabyte hard drive, or, for instance, I just bought the other day a 400 gigabyte hard drive. And incidentally, for those of you curious as to how much you should be paying these days, hardware storage has gotten so cheap that you should not really need to pay more than 35 cents per gigabyte. And I'll do the math. I'll let you do the math, but I paid, I think, $60, $80 for a 400 gigabyte drive just a couple of weeks ago. Anyhow, there is one other type of memory in this picture already, is RAM. And again, we'll revisit this next week. But whereas hard drives store your programs permanently, RAM stores them temporarily. Which is to say, there's sort of a path from your hard disk to RAM all the way down to your CPU. Hard disks, though huge these days, are relatively slow. In the world of computers, anything that's mechanical and physically moves tends to be slower than something that's entirely electronic. Case in point, consider the RAM DIMMs that we passed around. No moving parts. No moving parts means it's entirely electronic and therefore is faster. But it does tend to be more expensive per gigabyte or per megabyte. So in a typical computer today, you might have 256 megabytes, perhaps, up to, for instance, in my machine, as I said, 2 gigabytes. But notice, much smaller than your actual hard disk space. So what happens, in effect, when you double-click Microsoft Word on your desktop or Internet Explorer or any program for that matter, it's stored permanently here. And again, we'll come back to this next week. It's loaded from there into RAM because RAM, though smaller, is faster. And in turn are the bits that represent Microsoft Word, for instance, fed a few at a time into the CPU so that you get the Microsoft Word window, so that you can start typing away. And anytime you, for instance, go to the File menu and click Save, well, your document that's currently in RAM because it's fast and that's where you want stuff when you're using it, will then get saved back to your hard drive. So again, to be clear, we began tonight by looking at some of the most basic building blocks of computers. How do you store a number? We moved from there to say, how do you store a letter? And in effect, how do you store programs? How these zeros and ones are laid out, not that interesting for our purposes, but that they can be laid out, and we've seen how you might lay them out, is the interesting lesson. What we will do next week in our second of hardware lectures, if you choose to rejoin us, is focus more on this pathway, but also on a more consumer level. When you go to a store to buy a computer, what kinds of numbers do you want to look for? What kinds of hardware do you want to look for? And when you have the option of an ATA drive, an ATA 5, an ATA 6, a SATA drive, all of this stuff that you can read right off of the labels in CompUSA, Best Buy, or Dell's catalog, what does it all mean? That's where we'll go in our second lecture on hardware, the highest level, the real-world level, the consumer level of things. So I will stick around for a while, either up front or in back, as will the teaching fellows. Otherwise, we hope to see you next Wednesday. Please leave any forms with your handiwork on them at the door on the way out.